All right, so we're going to go ahead and begin our last unit that's covered on the AP exam, which is waves along with oscillations, also known as simple harmonic motion. All right, so we're going to start here with simple harmonic motion, which is a form of an oscillation. And really what we have with simple harmonic motion is just a situation where an object is undergoing through a repetitive motion with a constant time interval. The two big examples we're going to talk about are pendulums swinging back and forth, and masses on springs that are oscillating back and forth. Now, there is a slightly more technical definition, and we'll talk about this a little bit. But the more technical definition for simple harmonic motion is that the what's called the restoring force, or whatever is bringing the object back to its center point, its equilibrium, whether that's gravity in the case of the pendulum, which makes it swing back to its lowest point, or the spring force in the case of an object on a spring oscillating back and forth. But that restoring force is proportional to the displacement. And so a great example of this, unsurprisingly, is the spring force. We see that the amount of force we have acting on the object is proportional to how much the spring is stretched or compressed. Therefore, the restoring force is directly proportional to the displacement. And so springs are one great example of simple harmonic motion. Pendulums are going to be our other big example. And so we see here, as I said, our two examples. We have our pendulum that swings back and forth. Here's like that center position, which we'll call equilibrium, and we'll get into some of those definitions in a second. It swings out to this point, back to equilibrium, out to this point, and so on. And then here's our spring oscillating up and down. All right, and this shows it going down, oscillating back up. So both are examples of simple harmonic motion. All right, so let's go through a few definitions that we're going to use as we go through this unit. So the first is equilibrium. So equilibrium is basically the center point of our oscillation, the middle of it. It also would be the point where there is no net force acting on the object. So whether it's the bottom of the swing for our pendulum, or it's the point where the spring is not stretched or compressed at all as it oscillates back and forth. That middle point is equilibrium. Amplitude is going to be the maximum displacement from the equilibrium. It's typically measured in meters. We could talk about the amplitude in terms of degrees for pendulums, but what we should know in both cases is that is where there's the greatest net force acting on the object. We talked about how with simple harmonic motion the net force is proportional to the distance of its displacement, its distance from equilibrium. So if it's at its greatest displacement, it therefore must also have its greatest possible force. So that occurs at the amplitude. So here we have a quick video showing the object oscillating back and forth, and this kind of gets at what we were talking about before. We see that restoring force increases as the position increases, and that really is that idea of simple harmonic motion. We know that the further it is from its equilibrium position, the greater the restoring force. And so we can see two of the things we were talking about before. This here is the equilibrium position, and then when it swings out here or out here, that would be considered the amplitude, that maximum displacement. Two other quantities that we're going to define for simple harmonic motion, those are the period and the frequency. So period is something we've talked about before. We have some idea of it, but the period is the time for one complete oscillation measured in seconds. We talked about this for objects in orbit, but it works for oscillations or objects undergoing simple harmonic motion as well. We typically abbreviate period with a capital T here. The reason why it's a capital T is it is a time, but since it's a specific amount of time, we make it a capital T as opposed to a lowercase. The other quantity that we're going to talk about is the frequency, and we didn't talk about that as much with planets in orbit, but we could have talked about it there, but we will definitely talk about it here for simple harmonic motion, and that really is a measure of how frequently oscillations occur, or the number of oscillations per second. This is typically measured in units of hertz, which is just abbreviated Hz. You may notice that period and frequency are kind of like the flip of each other. I always think about it as period is the time for one oscillation, and frequency is the number of oscillations per time, typically per second. That's what 1 hertz is one oscillation per second. So they are related with this equation down here, that frequency is just 1 over the period. So we can find one from the other. We also could say, if we really wanted to, just rearranging this equation, that period is 1 over frequency. So frequency is 1 over period is 1 over frequency. All right, so we do have 2 equations for being able to find the period of our 2 big examples of simple harmonic motion, both pendulums and springs. I will spare you the long derivation for how we actually get to these 2 equations, but these are our 2 equations. The period of a pendulum is 2 pi times the square root of L over G, where L is the length of the pendulum, and G, of course, is just our regular old acceleration due to gravity. We also have the period for a spring is 2 pi times the square root of m over k, where m is the mass of the spring, or the mass of the object that's oscillating on the spring, and k is the spring constant. So these will both allow us to calculate the period for either one of those examples of simple harmonic motion. We, of course, then can calculate the frequency based upon that period. All right, 2 really important things I want to point out here with this is for a pendulum, only the length of the pendulum and gravity matters. Okay, those are the only 2 things that affect the period of oscillation for a pendulum. The mass is completely irrelevant, and you should have seen that in your lab that you did, that pendulum introduction lab. You should have seen that changing the mass had no impact whatsoever, but changing the length absolutely did, and we ultimately should have been able to get to the fact that the period, t, is going to be proportional to the square root of the length. Okay, we see, and we could rearrange this as t equals 2 pi over root g times the square root of L. All right, so we can see that relationship. The only thing that we can really control that changes that period is the length, because we obviously can't control g, and 2 pi is a constant. For the mass on a spring, only the mass and the spring constant matter. So mass does matter if we're thinking about the period of oscillation of that mass on a spring, but the thing that doesn't matter in both cases is the amplitude. All right, and that's actually a really important feature of both of these. It doesn't matter how far it's pulled, whether it's a really small oscillation or a really large oscillation. The amplitude is irrelevant. And the way I kind of always justify that in my mind is when you have a really, really small amplitude, it oscillates back and forth very slowly, but it doesn't have very far to travel. When you have a really, really big amplitude, it's going to oscillate back and forth much more rapidly. However, it has to cover a bigger space, so the time it takes to make one full oscillation remains the same in both cases. All right, so for this practice problem, we want to determine the frequency of oscillation of a swing. That just acts like a simple pendulum. They're actually a great example of one. And based off of what we know, the frequency should only depend on the length of the swing. And that's all we're given here, but that's enough to find it. So let's start by first finding our period. We don't have an equation that takes us directly to frequency. So I'm going to start with just period here. And so I'm going to say that the period is going to be 2 pi times the square root of 2 over g, which is 9.8. I plug that in and I get a period here of 2.837 seconds. Okay. Once I have that period, I know that frequency is just 1 divided by the period. So frequency is 1 over that 2.837. And so I end up getting a frequency here of 0.35 hertz. Moving on to this next problem, we have a mass oscillating left and right, and we want to know how the period would change if we change a number of things about that oscillation. So this is one of those problems where we want to set up our new and our original here. So for my original, I'm going to say the period is just 2 pi times the square root of m over k. That would be what our period is, and now we're going to set up our new situations here. All right, so how would the period change if the mass were tripled? I'll call that t prime. That's going to be equal to 2 pi times the square root of 3m over k. We can see the one difference here is that 3, and like I like to do, I'm going to pull that out in front, and so I'm going to say t prime equals root 3, it's got to stay under that square root, times 2 pi times the square root of m over k, which was our original period. So for the first one, it's just going to be root 3 times that original period. Moving on to B, what would happen if the amplitude was doubled? We know, and we can see from that equation, that amplitude does not matter. Okay, it does not affect the period, and so the period wouldn't change at all here. It would still be equal to t. If you want to write t prime equals t, that's fine, or just say it doesn't change. Lastly, if the spring constant were halved, that one will have an impact. So I'm going to say 2 pi times the square root of m over 1/2 k. Once again, I'm going to remove that 1/2, pull it out in front, and get t prime equals the square root of, and this is going to be a little weird, so it's a fraction, but it was on the bottom of this fraction, so it's really the square root of 1 over 1/2 times 2 pi times the square root of m over k. That double fraction can be rectified to just be 2. Okay, dividing by 1/2 is the same as multiplying by 2, so this is really just root 2 times my original period, which was t. Your kind of logic check that you can think about for this one, if we were to reduce this spring constant k here, that would increase our period. So it makes sense that it's root 2 times k rather than, or root 2 times t rather than t divided by root 2. All right, so for this last question we have, we're basically comparing our two forms of oscillation, the mass that oscillates up and down, along with the pendulum that oscillates back and forth. And so what we want to think about for this one is we want to think about how changing different parameters changes the period of oscillation. So initially they have the same period of oscillation, so just as a quick refresher for a pendulum, period of oscillation is 2 pi times the square root of L over G. For a mass on a spring, it's going to be 2 pi times the square root of M over K. And our first question here asks if the hanging mass is doubled for each, but everything else stays the same, will their periods still be the same? So they initially were the same, we're going to double the mass of all of them, are they still the same? And so what we see here is that for the pendulum, 2 pi times the square root of L over G, doubling the mass has no impact whatsoever. However, for the mass on a spring, it very much does change the period. And so the answer here would be no, they still won't be the same, because changing the mass will affect the mass on a spring. However, it won't change the period for the pendulum, and therefore they won't be the same anymore. All right, moving on to the second one. For this one, we're changing the initial displacements for each object. We're doubling it, but keeping everything else the same. So we want to know if that will change the period. And we see here that in both cases, amplitude is not something that impacts the period. So doubling the amplitude for each will not change either one, and therefore they still will both be the same. All right, so for part C, we want to know an expression for the length of the string that will allow the two objects to oscillate with the same period. So I'm going to take these two expressions for period that we had above and set them equal to each other. So I'm going to say 2 pi times the square root of L over G, the period for the pendulum, equals 2 pi times the square root of M over K, which is the period for the mass on the spring. We can see here two things happen. First of all, we can get rid of the 2 pi's, and then we can actually square both sides to get rid of the square roots. And so what I'm left with is L over G equals M over K, which means that the length will be equal to mg over K. Notice we do have this d, the displacement term, in there. However, that has no impact on the period itself, so that doesn't really matter what the value of that is.